example. So, weighting as the third topic. Maybe we have a fourth class on weighting, even that's really important, but the third topic in representation. Last time we talked about what is a term. We had stop words, we had stemming to see different word forms. They come together to make a term, like house, this houses, Häuser, tree, trees, will come together to make one term tree, one stem tree. And now we come to the second question. What is the contribution of one term for a document? How can we quantify that? How can we assign a number to this contribution? How good does this term represent the content? And for that we have many, many weighting models, and we'll discuss 2 or 3 of the basic issues within this process. Basic idea has been proposed by Keith van Rijsbergen, old important IR people. He said, by Loon and Rijsbergen cited him. And Rijsbergen is already quite old, now retired already. He said, it is proposed here that the frequency of word occurrence, that's the main issue, is in an article, furnishes a useful measurement of word significance. So a lot of information here. He said, what is the contribution of a word? He calls that word significance for a article or a document, as we call it. And for that we use the frequency of word occurrence. So basically, that's what we said in the first class. We count the occurrences of words in documents. And Loon says this is something useful we can use. Remember our example? We had already counted the words. Now we know that, yes, this can be Wolf or Wölfe, or this Wolfes can be different forms, but it's all the term wolf. We don't have stop words here. We have our query, and now we have the question of what is the number 1 ranked document here. And our first assumption was to count the occurrences for the 2 query words. We have 2 query words, and let's count them both together, make a sum, again an assumption, and we had the question, maybe this is a good article, it's balanced, we said. Or is this a good article because there's a higher overall number, but doesn't contain one of the keywords, right? So we had some doubts here. In the question whether this or this document with 6 occurrences of both term verbs together is better or worse, so it should be on number 1, can only be resolved with weighting. Right? We have to make a decision on what is the contribution. So basically we have a weight, we can imagine a weight, and for a specific term and document. Okay, let's see, and then we can do things like you learned already in the introduction class. We have a query, we have a vector space model. When it comes to models, we will elaborate on that, we will revisit that with much more time. But here we have a weight of a term. This axis represents a term, maybe Wolf or Niedersachsen, and the weight we can count and assign a weight to a document at one of the axes here, one of the dimensions of our vector space. And for that we need to calculate our weight. Now, how do we get the weights? Okay? Different approaches, formally, heuristically, empirically, maybe based on relevance judgment, something we will talk in the optimization class. But today we talk about empirical measurement. Basically, I count how often is it there, and then do something with this pure frequency. So as I said, the main question is how good does a term represent a document? And now the first assumption, of course, is I just count. Okay, if it's 5 times there, it is more important than if it only occurs 1 time or 4 times. So we have a notation here, formula, term frequency, TF, is just simply the number of occurrences. How often does it occur in document N? And that is our term frequency. So that basically says the more often it appears, the more, the better, or the more important this term is for the document. Okay? Basically, absolutely straightforward. Now, what about the relationship between the weight and the number of occurrences, right? The number of occurrences is just a natural number, a normal, regular integer number. But how could it relate to the weight? Is it really the more often it is in the word, the more important? What about the second appearance, the third appearance of a word, the thousandth appearance of a word? Should that also be equally important? Document. Here it's word appears 1 time, here it appears 10 times, 100 times, 1,000 times. Is this 10 times more significant? And is this 10 times more significant? The right to the left of it. If you look at these relationships. What do you think? You are users of IR systems. Yes, we should always, if we believe what Lund said in Kreisberg cited, we would say, yeah, this might be the best hit, but is it really 10 times more important, 10 times better, if we have the word 1,000 times instead of 100 times? No? No? You shake your heads? Why not?
Because the quantity doesn't matter about what's in the document.
Yeah, we don't talk about quality and things. Of course, as a user, we read a text completely different. For quality, the real information, is it there? But that's something that is difficult to grasp for the machine. The machine can only count, unfortunately. So it's left with these numbers. Is it really 10 times more important in this case than in this case? What do you think?
You wouldn't say that you would assign the same amount of weight to every occurrence of a certain word in the text, but with more occurrences, you would rather choose a much lower weighting for this one.
We can count, okay, occurrences, as you said. Then I would say, okay, the first gets a certain amount of weight, and the next should get a second occurrence gets a
lower amount.
A smaller weight than this one, right?
Yeah.
So it would be like that. And the third? Even though. So adds less. The word is already in the document, right? If it 10 times there, just doesn't bring so much more information. So the weight should not be very much higher. Remember, and in our example, if we look here, that would lead to a situation where these 5 occurrences would not be so valid as 3 plus 3. We would, in this case, prefer the balanced document, as I said, somebody mentioned it, you, I think, in one of the first classes. 5, it's a bit more than 4. but it's not so much more, worth more. Okay, and that's exactly what is done in weighting. Very good. So the first occurrence is important, yeah, the word is there. The second, not so important, less important, and it gets less and less contribution to the weight. So we get a curve. Don't make me draw too much. How does it look like? What is this function called? No. It's one of very few cases where we need something from mathematics which has not been taught in basic schools in the first 4 years. Usually with 4 years of school you can understand all the formulas here, but in this case no. Yeah? Yes, yes, it's an asymptotic curve that approaches like a asymptotic curve approaches something but never reaches it. It doesn't get beyond a certain degree. For this, that's not true, I think, for this function. But don't ask me too much about the features of this function. What is it called? No, just fixing the hair is not going to end, I think. Yeah. What is it? It's the logarithm. Logarithmic function that increases over time, but the steps get smaller and smaller. And there's an approximation for us that we can use throughout the class for the logarithmics, and that is more intuitive. Like you said, the first is worth, okay, it's 1, the second is less. So the contribution depends on the position, right? The fourth position has a lower contribution. And if numbers increase and the contribution is lower, how can we model that? How can we, if we have a certain amount of work and we want to that one person does in one day, we want to have it done faster, what do we do? We add more people, and then how do we calculate the work hours? Well, division, right? We divide by this number of occurrences, 1 through n. So we have the weight is 1 plus 1. What is it? 1/2 for the second half. For the third, 1/3. For the fourth, 1/4, and so forth until 1n. Okay? It's a very straight formula. And this is called the harmonic sum. It's on the slide, you don't have to note it down. And that's a nice approximation that we can use for the logarithm. That's how we deal with word occurrences. Okay? It's there 10 times. No, it's not. The weight is not 10. It's the harmonic sum of 1 plus 1/2, 1/3 until 1/10. Because a 10th occurrence doesn't really add much information for me. Here we have a harmonic sum, similar to the logarithm, the contribution that each occurrence, as you said, brings to our weight to model the importance of the document. Here we have some examples. Okay. Now we can look into our example where what would be the number 1 ranked document now. Of course, this is not the end of the class, yes, but this is just preliminary result. But what is it? Let's make this red. For example, let's calculate the logarithm harmonic sum for f, and E. Okay? We can compare F and E. We would have for F, let's see, document E. The weight of the term wolf in document E was, I think, 4 occurrences, right? So, no, here we have it. Yes, and then we have 1 plus 1/2, we have 2.0. Then we need the weight of the term Niedersachsen, and that is in document E. Well, the number of occurrences was
2.
2. So
1.5.
excellent. Very good. 1.5. Yes. And now the same for document F, I think it was. We have the weight of the wolf for document F is what was it? Wolf in Niedersachsen. Well, it was 3, right? So 1.8. And the wolf and the weight of the Niedersachsen in document F is also 1.8, was also 3. And now we can see what would be a better match of these two. If we calculate, can we calculate this now? We have not dealt with models yet, so different ways, of course, now to calculate it. We can do the sum, very simple. Then we would end up with 3.5, and here we point. Sorry, I'm doing all the German way, decimal point, and here we have 3.6. So document F would be the first hint. If we do the sum, right? We don't have to. If we do the multiplication, probably also, right? 1.8 times 1.8 should be, must be, basically. Okay, so now we have a way to decide if the sum of occurrences is equal. Even if it's not equal, we use the this weighting scheme. Okay, questions? So the more balanced document will win. But that's not all to weighting, but a very important issue. The next question is, well, is Wolf and Niedersachsen really to be dealt with identical? Now the question is, are all terms really equal? Yes? Please. The higher one. Yes. Document F has a higher weight if we sum up. But we haven't talked about models, so we just use the sum for the moment. Yeah? And you can do the calculation for the other ones. 5 and 1 documents will also be lower, like this case. A will be positioned behind these two at least, okay? Anyway, so further questions? Feel free to, Belize, yes. We calculate the weight with the logarithm of normally, but we use the harmonic sum. So if we have 3 occurrences, we say it's The first counts fully, the second counts half, the third counts 1/3, the fourth 1/4. And if we build the sum, in this case 4 occurrences, that's 2.0. And here is the example for the harmonic sum for the results from 1 to 10. Okay? So I didn't do the calculation really, I just read it from this table, but basically we would do this sum. Here for Wolf and Niedersachsen we had, what was it? We can do it for one example, so maybe it's better. We had E, document E, for example, has Niedersachsen 2 times, 2 occurrences. That means I have to do 1 plus 1/2 makes 1.5. Okay? And here, yes, we have 1.5 correctly. Straightforward, right? Or if you don't understand it, just ask again. Not the case. Okay, so that's the first approach to weighting. Now we treated all terms equally. Another question is it really fair to treat all terms equally? Is Niedersachsen and Wolf basically the same information? Does it tell us the same about the document if Niedersachsen or Wolf is contained? Further question? Ask. Please. And she explained it? Okay. Hopefully better than me. If you understood it now, it's okay. If not, you can still ask.
Can you just repeat it and try to explain it?
Okay, sure. So we have these documents. We only look at E and F. Only E and F. Now we want to find out. Maybe we need light? So just going out. Can you see it, or do we need light? Light? Yes? Licht Mitte, Licht außen. Better? Oh no? Not really? Ask everybody to sit here because of the slides, and now I have using the board. Let's see if it can read. So we had document E. We read the number of occurrences for Wolf. It is how often? 4. In Niedersachsen? 2. Now we calculate the weight for, how did we do it? Wolf, or let's start with Niedersachsen. Sorry, Niedersachsen for document E. It's 2. The first counts fully, the second counts only half. 1.5. Now I calculated for Wolf, for document E, 4 times. Now I have 4 contributions. First is fully, second is half, third is 1/3 plus 1/4. 1.5 plus 3.3 plus 1.25. I looked it up in the table, right? 1.83, 2.08, I think. 2.08, and we don't look for too great exactness, so 2.0 is okay. Okay? And now I do the same thing for document F. And there both occurrences are 3 times, right? Remember? Then I do this calculation. 1 plus 1/2 plus 3.3 makes 1.88. No, wrong. 1 point, what is it? 83 should be, right? Okay? Better now? Good. Make sure you understand the basics things add up and add up. Okay? Now, again, we are there with, we want to know, is it really fair to use the same weight for Niedersachsen and Wolf? And maybe here this is not such a good example, but consider the differences between words. Consider a word like man and a word like another word. Any examples? Grexit. Let's say Grexit. In a text collection from last year. Until last year, from the 1960s until last year, what is the difference between the word Grexit and the word man? Well, straightforward.
Man has a lot of purposes in the text and can be used in different contexts, while Grexit is very specific.
Yeah, ambiguous. That's very specific, yes. That's something that's difficult for the computer. We will see how we can try to capture that in later classes. But for the moment, if we just count words, what is the difference then? No? But you know it? No? What is the difference between man and Grexit? Well,
If you just count it, then it's no different.
it's
no different.
there is.
No different.
Really?
If you just count it
If we count it, where do we get a larger number?
against a man.
I guess two, right?
If we look in German,
of course.
next.
Yes, if we look in German text, there's the English class, so let's say the word man, okay? Maybe I should use my English examples. But I guess it's straightforward that the word man will appear many, many more times. Right? Brexit had just been invented. It's not in the newspaper before last year. So around very few occurrences, and we found very, very many. So there are huge differences in the number of times a word appears. Very big differences, okay? Now, which word gives me more information? Grexit or man? Or man? Grexit is familiar to everybody, right? No, not really. Sorry, it's an artificial word to use for the exit of Greece from the euro. A potential exit, right? So it's a very new word, doesn't appear very often, that's why I used it here. So, which of the words gives us more information? Specific, yeah.
For a text about men, that wouldn't appear so much.
It appears very often.
Yeah, but if you say specific about men,
Yeah. Well, look, we don't even know what we're looking for when we look for man, right? Quite stumpy. Could even be a stop word. It's almost a stop word, let's say. So if I have a collection of documents, I will have a small set with Brexit. I have a huge set with man. Then it's clear, man doesn't tell me anything. It doesn't distinguish well. It's almost in every document. Maybe not in all. Think of another example, right? But in Grexit, we can say Grexit is in a way highly informative because it gives you a very small set. So rare words, in a way, have more information because they distinguish much better. And now, of course, they have the disadvantage that the set is so small that I find very few documents, right? But that might even be also positive. So there's huge differences between man and Grexit. And let's explore this further. If we map all the words on a graph sorted by the number of times they appear. Ah, here it is. This is closest to most people, so let's do this one. Let's see, we order all the words. This is the most frequent word, the second most frequent word, and this is the rarest word, position N, right? These are words that don't exist, of course, count not 0, that's not important. They have a word count, they appear how often? The last frequent word, least frequent word appears probably, how many times? One, maybe. Very likely one time, right? That's for sure, but we don't know how often the most frequent word appears. Depends on how many texts we have and stuff like that. But let's assume it's a number x, the most frequent word, then the second, third, until number 1. Okay? Very straightforward. We sorted them already. Now, how does this curve look like? It's like a step function, right? 1, maybe 2. We can make a asymptotic, as you say, curve. Could look like this, or it could be like this, or like this. How does it look like? Everybody who deals with language should know about this. How often do words occur? Aha! Say it's more like this? Uh-huh. Other opinions? Everybody agrees with this assumption? What would that mean compared to such a solution? That would mean that so just a very few words that appear very often, and then we have rare words very quickly. And this would mean it's a linear distribution, right? And this would mean, well, it's almost equal distribution, like in a social society, social democratic society. Most people have the same wage. Nobody has really high wage, and everybody is almost the same. And then there's only few people who have a smaller wage, equal distribution, right? And this would be a very unequal distribution if we talk about wage, which in most people have nothing, and only a few persons have an extremely high income compared to these guys here, right? So how do words appear? We have only one vote so far for the extreme distribution. What do you think? What about computational linguistics people have in the class? Anybody visited the class? Any information there? No? Well, that's how words are actually distributed. You're absolutely right. Maybe even more extreme as I have drawn it here. It's that there are a few words, a few hundred words that appear very often. And then we have only small numbers until the end. That means like most or half of the words, or more than half of the words, appear very infrequently. A few times in a collection, in a large collection. We're talking about large collections here. And then we can observe this behavior. And it's very regular. We don't have any jumps here. It's a very smooth curve if we have a large corpus. Why is that? We could ask, why is that? Because of economic reasons, our brain wants to memorize as few words as possible. So there are a few words that everybody knows that are used all the time, right, for language economic reasons. And now this makes a huge impact on information retrieval, because this case that I've shown with Brexit and man, very frequent, very infrequent, the difference is dramatic. Brexit, man. This is a few numbers of maybe 10 times, order of 10 times 10 times 10 more often, a more frequent word will appear than an infrequent word. So millions of times more. And that's why we have to deal with this. This is called the Zipf distribution. The first behavioral scientists to model that was called Zipf. Now we can ask what is a good term, and we already noticed that these are not very good for querying because they're almost in every document. So in this middle chunk we have a good informativeness. These are very good terms to distinguish sets of documents. They give me a good separation. If I have a large set and I ask a small set, maybe 2 terms, I will get a very small set very quickly. And that is informativeness. I exclude like 99% of the documents. If I exclude 2%, and I stay with 98% because I have a high frequency term, not so good, right? And Zipf said, well, of course, also these words are not so good because they give me so few documents. So we have a curve like this, as we can see it here, Zipf's law. And we have the words ranked by their order, the frequency of words, just like there. And this is a good chunk for good terms, informative terms. So how can we model something, a metric of informativeness? Let's give it a metric. And then we're almost there with our second most important weighting factor. A term is more informative if it appears in what is it? Yeah? Few documents, right. So I could say the more informative, if I have n documents, the whole set is n, and this is n, then something like n divided by n could be used to measure informativeness, or vice versa, n divided by n. If this is small, informativeness is high, right? Small n, high informativeness, large number, low informativeness. For example, n, and I have a word that is in every document, n by n is 1, would be the lowest number in this case if it's unnormalized. Next class we talk about the normalization of this. Then we have a bad informativeness. We can call this the discriminatory power. How can we well distinguish between sets of documents, distinguish documents in the set? Just by this metric, n divided by n, as was suggested here from the auditorium. And we have a nice metric here. And this is the second most important metric for weighting and information retrieval. It's called inverse document frequency. The frequency in how many documents does this word occur? Inverse, 1 divided, or n divided by the number of documents in which it occurs, which would be our small n here. And as I said, yes, it makes sense. So we end up with inverse document frequency, number of documents in the collection, number of documents in which this occurs. The higher this is, the more informative the term is. Now again, we can come back to our example. I looked it up, at least according to Google. Wolf is much more frequent. Not much more frequent, but quite 20 times more frequent, no, not 20, almost 10 times more frequent than Niedersachsen. So what is a better query term? What gives me more discriminatory power? Niedersachsen, yes, exactly. Right? In this case, we did everything right. We didn't split up Niedersachsen in Nieder and Sachsen. Let's assume that the stemming worked fine, and we noticed that it's an entity, it's important. So Niedersachsen is a better search term. So it's given a higher weight.
But before we said that the one who has more,
More hits?
but now we say the one who has few.
Yeah. Fewer hits is better. Because if I have more hits, imagine a word like Mann that is in 95% of all documents. I get back almost the whole collection. What is that's no use for me. But another argument, please. Yeah, please.
When you were calculating the document E and document F, I asked you if you said the one which is higher.
Yes. And there's a difference. Is in the document, in one document. Now we talk about the collection. Right? We talk about the collection of all documents. We have many, many documents. And if it's in the document, very often Wolf, then this contributes for the weight. Then the weight goes up. But if Wolf is very often in other documents, the weight goes down. Right? I want hits where my term is very frequent, but not in other terms, in other documents. I want documents where my term is frequent, so term frequency should be high, but inverse document frequency should be low. I don't want the whole collection as an answer. I want a
What was it called What was it called?
inverse document frequency. Yes, just back. It should be high in the document, but not in the collection. Right? If I ask with the word Tisch or Deutschland in a newspaper collection, Germany newspaper collection, it's very frequent in a German newspaper. Doesn't distinguish well, doesn't help me a lot. But if I find a good term, Grexit maybe, or whatever very rare term, that helps me. And if this rare term like Grexit is frequent in the document even, if it appears 10 times, that's very nice. And probably it's about my topic, right? Not necessarily, right? Because, of course, we're just doing calculation here. We don't understand the document and anything like that. A human can always have a different opinion, but for the machine, that's how it is done. Okay, so we have TF, now we have IDF. Okay, further questions about this? Understood? Okay. In a way, of course, we always want a lot of results, but, well, not really, right? So the term is not so good. Here I did the example calculation. Let's just assume the Google index is 10 billion documents. I have no idea, nobody knows. And then we have, at least Google says Wolf has 500 million occurrences, Niedersachsen have 85 million occurrences. So both are not very good terms, but there's still a difference between them. Wolf, Niedersachsen, as we said, is a better term. It should be given a higher weight. And how can we calculate that? We divide 10 billion or 10,000 million by 510 or by 85. And we get the IDF, the inverse document frequency of both terms. And we see that the IDF of Niedersachsen is higher than of Wolf. So more than less 5 times higher. So now, question now. Niedersachsen will be ranked 5, the term will be 5 times more worth than the term Wolf. Okay? So again, we come to a different weighting now. Wolf is given more credit. Here we have it. And with this we come to a very simple weighting scheme. It's called TF-IDF, simply the multiplication of TF and IDF. Okay? And now we can go back to our example. Let's see what happens in our Wolf and Niedersachsen example with documents E and document F. Remember we had E, I think, was 4 times Wolf or Niedersachsen? What was it? Wolf, no? You correct me if it's wrong. F 3. Remember? Now we have a new weighting scheme. The weight is now TF multiplied with IDF. So the weight for Wolf in the document F is the TF, that was 1.8, right? Correct? Yes, okay. And the IDF now, let's assume normalized, we have an IDF of, that's something that is stable. For any document, they have an IDF of Wolf and an IDF of Niedersachsen. And this was, which was 5 times higher? Niedersachsen, right? So this is 1, 0.2. Or even make it simple. 5 and 1. Okay? Just for simplicity. And now, so Wolf, IDF 1 times 1 is 1.8. Now we come to the weight of Niedersachsen for document F. 1.8. But now Niedersachsen is better. So it gets a higher IDF. And then we end up with 9, something around 9, right? Yes, 9, exactly 9. 1.8 times 5. TF multiplied with IDF, 1.8 multiplied with 5. IDF, we get weight of document E. Weight of Wolf in E was 2.0. 2.0 times 1 is 2.0. And now comes the Niedersachsen, which was 2 occurrences, right? Remember? It's 1.5, 1 plus 1/2 is the TF, and now comes the IDF, 5. 7.5. So we have a contribution of 2 and 0.5, and here we have a contribution of 1.8 and 9.
Where did you get the 1 and the 5?
Okay. IDF, that's more or less an assumption. As I said here, I checked in Google, and we have assumed 10 billion documents and 500 million occurrences, 80 million occurrences. We know that the IDF of Niedersachsen is 5 times higher. So I put 5 and 1, just to make it simple. Of course, for the next homework, not this time, but next time you will have to calculate something like that. It will be not as simple. It will be more tricky. But anyway. So this is 5 times better term, because it's less frequent. Okay? And now which document would be ranked higher? Let's assume we make the sum, 9.5, 10.8. Again, document F would be ranked higher. Okay? Everything stays the same. But if it would be vice versa, if we have a document now, let's check document A. Let's do the same calculation for document A. How do we have to do it? A would have been third if we do just TF. Now we do TF IDF. We have the weight of Wolf in R and the weight of Niedersachsen in R is, for Wolf we have 1 times 1, and for Niedersachsen we have 5. The harmonic sum of 5 was, I look it up, 2.28. Times 5. Almost 2.3. So this is 11. And now the sum is 12. So if we use DF-IDF weighting, document A is the first hit. Okay? If we just use TF, it's the third out of A, E, and F. Because it has the rare term very often, and that is honored by IDF. Okay? Questions? So far, understood? Then, what else should we consider if we talk about the numbers here? What about the IDF? Now, every occurrence counts. The more occurrences in the document frequency, the more often it is used. What could we introduce for IDF? What is the difference between 1 million occurrences, 10 million occurrences, 100 million occurrences? Is it so important? Well, same story as for TF. We should use a dampening factor. We could use a logarithm or harmonic sum. Because we have very large numbers, we should not have such high weights.
What about document D now?
Uh-huh.
I guess it could be more than F or A.
No, we have E, we have calculated E.
D.
D! Ah, yeah, yeah.
8 times.
Yeah, D could also win now very much, yes. And here we should have we must have more intelligent weighting we see now. What is E? Let's see. Good question. ED. Huh? We have weight of Wolf in D is 0. And weight of Niedersachsen is now 5 times 8. That's a good question. 8, 2.7. 8 times 2.7 is 16, 21 something, right? So it's higher, would be ranked higher, yes. Not very nice. Right? Not the very nice effect of TF-IDF. So this factor of 1 to 5 is very high, right? It favors the infrequent words very much, even if the other word doesn't appear. That could be later taken care of by the matching function. Because who tells me that I have to do a sum? I could also use a product. And then this document would be out because it has 1 0. Right? And there are other matching schemes that are better than the sum here. But yes, if we use pure TF-IDF, would be a problem. And the main issue why it's a problem is that we have a difference between 1 and 5 which is very high. So in practice, we should also use a logarithm here or harmonic sum for the IDF. And that is also done in practice. IDF is also typically logarithmed before it is used. As we see here, we have the logarithm of number of documents and the number of terms. So this is n through n, as we have learned it already. For example, for the web, 100 billion to 500 million times, what was it, Niedersachsen? Logarithm, we cut the effect of very low frequent terms. Okay? But we don't do the full calculation now again. All right, maybe next time we do it for practicing. And here again, the logarithm here, the natural logarithm, and just for you to see the curve. And always we have to be aware that there is no defined logarithm for 0, so we also have to do the logarithm of 1 plus n whatever, right? But in this case, 1 plus the number of documents in the collection. No, that's not 0. But for term frequency, if we use term frequency, we can do it for 0. Okay. So TF-IDF, both can have a logarithm, and we have a sum, and that's the weight for one term in one. Basically, we're doing already the ranking here, right, to illustrate this, but we're just talking about the weights right now, not about the matching algorithms. Yeah, very nice. We have two of the aspects. Now comes the third one. We still have plenty of time for the third aspect. So what else could be a relevant information if we talk about counting word occurrences? This is the next step. Now we also have differences between documents, right? And some documents can
shorter than the other documents, so that we have
yeah, we have to see it is we give the same term frequency to, now we have a term frequency of 10, for example, and we treat both in these both documents equally. We have a short document where Niedersachsen appears 10 times. We have a long document where Niedersachsen appears 10 times. And can that be dealt with equally, identically? Or do we have to do something about it? Which is the result you want? Or let's say, for which document is the term Niedersachsen more relevant, more, as Lund said, what was it, significant? Where does it tell us more about? If it appears 10 times in the short document or in the long document? Obviously in the... Oh? Really?
So because maybe in the short one you have to repeat it more, the same word, but there is no information.
Yes, that could also be an assumption that I say, this document is so short and it has 10 times Niedersachsen, that doesn't tell you. Right? But let's think of a document of maybe 1,000, 2,000 words and one of 100,000 words. And in 100,000 words with 10 times Niedersachsen, we don't even find it maybe. Then we have a 2,000 words and it's 10 times there. That's quite relevant, right? So I would say the short one. Okay, okay. Convinced you? You are satisfied also now with the shorter one? And also I don't want to read so much, of course. Longer documents might not be welcome anyway, but that's another question. But now the issue is the percentage of occurrences of the words that are Niedersachsen or query words is important, not the the pure count. Right? If I have the long document, I have 10 times. That doesn't say me the same thing as if I have a short document. I have 10 times the word Niedersachsen. So what do I have to do? What is the magic word here? We haven't heard it in the lecture, I think, so far. Well, how can we describe what we have to do? Long, short. Let's say 1,000 words, 10,000, 2,000, 200 words. And now we count words and we say, for example, there's one occurrence and one occurrence. When this is 1 out of 200, that's much more than 1 out of 10,000. It's better, right? What do we have to do with these documents? What would be the best for information retrieval? When would we not have to worry about document length? Huh? We don't have to worry about when all documents are the same length. Then we can just count, right? Okay? So why don't we make all documents identical in length in a mathematical way? And that's what we do. We do some calculations to make all documents of an equal length, and that process is called normalization. Normalization. So we normalize and assume all documents have the same length. Now, what could that length be? The optimal length is then, from a mathematical point of view, we also want to deal with probabilities. So the best length that we want to achieve is 1. All documents should have the length 1. And we make sure that they get transformed to the length 1. And then we have maybe a count of 1, and here we have a count of 2 of another word, a count of 5. How do we make this possible? How do we come from 10,000 to 1, from 200 to 1? What is then the TF if we have 5 as a word count? What would be the TF in a document of length 1? From 1 out of 200 to x out of 1, right? So this is what we need to do. So the weight would be, you can forget about that x, the weight, the new weight, or the new count would be 1 out of 200. And how can we have a general formula to do that? Let's develop it here. We have a, or maybe there's a slide. Don't have to work so hard here. Document length, yes. Here we have the document length, a nice example. We have 4 documents. Which one is the longest? Small toy examples, right? But which one is the longest? B? Aha. 9 plus 9, 18. Anybody longer? Not really, right? 18 words, 13 words. Okay, it's next. Now we want to give all the documents the length 1. So let's just show it. Here we have the short document, the long document, yes. And here we have 2 and 3. We think that Gerd, we should give document B because it counts more often. But if we consider the number in percentage, Gerd is more important for document A. And here we have normalized weight. All documents have the same length and the same influence and chance to be found. If I don't do length normalization, you will typically find more long documents than short documents. All right? The approach is divide all term weights by the length of the vector. The sum of the term length, we have A and B, and now we have a normalized version of A and B, which will be come up through our length normalization. 5 is the length of this document, 15 is the length of the second document, and we divide all word counts by the number of, by the length of the document C. Not much to it. And then we have 1/5, 2/5 from 1 to 2, and we have 18/15 from 8, and so forth. Now if we sum up the length of the documents, what do we get? The new sum is 1. True?
Yeah.
Also for both documents. Beautiful, all have the same length. That's what we wanted. All have the same chance to be found for the queries. Right? If I don't do length normalization, I will more often find the long document, no matter if it's relevant or not, and who knows. That's a important step also that brings much improvement in performance. And now, of course, we have a new problem. Maybe it is fair that longer documents are found more often because they simply contain more information. Right? And they really use a lot of weight. Now maybe you find the long documents very rarely, because there's always a short document which has the same word, and it has now a bias to be found. Now you find much more short documents. Again, we have a bias introduced. First it was the long, now it's the short documents. So we have to find some compromise, some trade-off. Okay? And that's why we don't do a complete radical length normalization, but we do a so-called pivoted length normalization, somewhere in between a biased length normalization, slope normalization. There's some factor that big documents are getting smaller, but not to 1, right? And short documents, they are made a bit longer, or the weights increase, but not too extreme. And that has to be done based on the differences on what is the maximum document length. Now we have to know what is the longest document, and then we balance it out. We have a factor that we can deal with, for example, which is called the slope parameter. And with the slope parameter, we say we want to make more or less length normalization. It should be all very close together, like all should be 1. All should be 1.1. And the other extreme would be just to take off a little bit or to do no length normalization. This value needs to be selected. Not all documents will now have the length of 1. It's not as beautiful and easy to make the sum as before. But there is a short, the long documents have still a chance to be found, and the short documents have more chance to be found than before. So this is kind of a compromise. And here is the formula. 1 minus slope plus slope times old normalization average old normalization. What does it mean? The average old normalization factor was between we have 2 documents. One was 5 and the other was 15. Remember? Very simple example. So the shortest and the longest document. So the scope that we had to normalize was 10. Right? For 10 we did something. And this is the old normalization factor. Average, actually the average length is 10. Right? And the slope factor is something that has to be chosen. We start with 0.75. We don't have to do anything else really. And now we have 1 minus slope, so 2.05 plus. So this is a factor that all the documents are given, all the weights are given. And then we end up with 7.5 times the old normalization, which was 10, divided by the average, the average length here. Our average is old normalization, and x is the term that we found in the regular normalization. Let's check it out. We end up with a pivoted length. How do we get the length? In this case, no, actually that's the result. We end, in this case, up with we had the lengths of 5 and 15, remember? Now the new normalization brings that to, not both to 1, 1 to 0.6 and 1 to 1.3. So now the long document is still longer, almost twice as long as the short document, but not 3 times, as it was in the case 5 and 15. Okay? We end up with a less extreme normalization. New length, that's actually the factor, and the new length is around 9 and 12, that's it. Sorry. And we can do the calculation. 8 divided by not 1, by what was it? Before we divided 8 by 15. Right? Now we divide 8 by the pivoted length, 1.3, and we get 6. So we cut down the influence of the long document, but not as extreme as before. And that would be the result in this case. Here we divide all the weights with the pivoted length, and the pivoted length is the result of the previous formula, this one, which takes into account the old and the new document length. So now we have to look at 2 slides to make this calculation, and we end up with these weights. And we see, the short terms, they even grow in importance, the count is increased, and for the long documents, the count is decreased. So that's the effect that we wanted to have. Pivoted length normalization, compromise between no length normalization and full length normalization. Okay, questions? Do we have time for questions? Well, some.
Excuse me, how do we get the new length 8 equals 9?
This is just by summing up. 6 plus 4 plus 1. 1.6 plus 3 plus 6. This is 6, 7. Maybe it's not correct, huh? Doesn't look correct, that's true. This looks correct, but here we have 6, 7, 8.
Yeah.
Should be 8. That's wrong. Good. So you saw the mistake. Hopefully I can correct it. So that is the pivoted length normalization. Bit complicated. Well, if you have to calculate anything, it's only will be the normal length normalization, of course, right? But you should have, of course, heard about it. And that's it. So we have a lot of parameters for weighting. We see we don't just count, but we interpret the numbers. We count the frequency of the term in the collection, in the document, right? And document length is something we use. And that all enters the formula. And this is a complex or more complex weighting scheme. We just had TF-IDF. I said, okay, we understand TF-IDF. We explain it. Why is it that way? And this is the so-called Okapi BM25 weighting model that is currently still, for last 10 years, one of the best performing models. So this is also implemented, and you should use it. Every system should use it. And when we look at it, we see it contains nothing else than what we've talked about so far. Right? Just a few more additional things. But here is a length normalization, document length of this document divided by the average length. Well, we've talked about that, right? Then there is TF and IDF. There's a lot of term frequencies also normalized in addition, and we have n, we have a logarithm, we have the document frequency, so we have something like the inverse document frequency in this formula as well. All the basic stuff that we talked about comes into one big formula. Here is another just way to look at it, a bit more simple. QTF is a query term frequency. We always assume it's 1, right? We don't worry about the query term frequency. So our formula would look even more straightforward. Okay, before we talk about the other problems, are there further questions? I think that we do another class on weighting next time, and we repeat some of that. So we may go through an example again, so you can calculate that, and doing that we'll introduce a few more details, but in principle these are the three most important factors: TF, IDF, document frequency, document length, sorry, right? And next time we see how we can use logarithm or harmonic sum for both TF and IDF, and how we can use the normalization for the IDF and some other additional weighting factor. But basically we just go through a longer example so you see it again, and this is all sticks in your head. As I said, you can easily memorize this when we go through a longer example, plus some additional stuff. Or are there further questions now? Oh, but this is the core of weighting. Remember all this. Yeah, please.
You told us that normalization and not slope normalization would be relevant for us in this course, basically. And my question would be, if it comes to the exam, do you provide us with some of the numbers? Because I'm not sure how detailed I can calculate 1 plus 1/2 plus 1/3 plus 1/4.
Ah, okay. Yeah. In this case, you would never have to do the calculation. You just write down 1 plus 1/2 plus 1/3, and the sense of the exam is not to do simple calculation that you could do on your calculator, but you don't have to just write it down as it is. In case there's something like this would be in the exam, you don't have to really calculate. Right? Just write down. That is a result already, right? The rest is something that anybody who can use a calculator can do. That's not what we want to teach you. Huh?
When do we get the exam from last year?
It's not yet there, no? Oh, okay, sorry about that. Yes, missed that. Will be soon available. Okay, hopefully I remember. If I don't do it in the next week, please send me an email, because once I'm out of class, I forgot it. So next time we do a longer example, and then there will be a homework for you to calculate based on this, and then we have done a very good step, and then we come to models. Now we have weights. How can we determine what is really the best hit, right? Do we multiply or do we make the sum? Like in your example, we saw that summing is not always very good, but there is much more to it, and that's it. Okay, so see you next week for more weighting.